Hello.
I am recording.
Yes. Yeah. Hello, and everyone. Welcome to MACSMIN. Now, Miloslav Torda, Dr. Miloslav Torda, will talk about symmetries of maximally dense plane group packings of regular convex polygons. Over to you, Mila, please.
Thank you, Vitaly. Thank you for inviting me to MACSMIN. So let's start. This talk is based on this work with Goulermas, Vitaly, and Graham Day. So all everything present here is this paper. So if anyone is interested, you can look those up there. So first, I want to some motivation why to study crystallographic packings. Motivation came from science and chemistry. And specifically the problem of crystal structure prediction, where given specifically molecular crystal structure prediction, which is given a molecule and some pressure temperature conditions, we will predict the phases, stable crystal phases of the material. This boils down to, in most cases, to minimizing energy of a system of molecules. Our approach was to instead of minimizing energy, to minimize packing density. So what I mean is, let's say we have pentacene molecule. This is pentacene. The black dots represent carbon atoms. The blue dots represent hydrogen atoms. And we want to predict in what crystal phases, in what configurations the pentacene molecule crystallize. So this is so I found this configuration in literature. One actually some chemists made this thin film, pentacene thin film on graphite surface. And two, I found it also as a configuration found by molecular dynamics simulation driven by the Lennard-Jones potential. So what we want to do, instead of minimizing, for example, the Lennard-Jones of this system, we represent the pentacene molecule by an non-regular octagon and find the densest packing of this representation. So since we are interested in crystals and periodic crystals, and the model for periodic crystals is a crystallographic symmetry group. That is a group, discrete group of isometries containing a lattice subgroup. We introduced the crystallographic symmetry group packing. That is given a K, a compact subset of the Euclidean space, and G, a crystallographic symmetry group. Crystallographic symmetry group packing is a collection of copies K generated as orbits generated by the action of the crystallographic symmetry group on Rm. So here is an example of a crystallographic symmetry group packing of pentagons in the plane group P2MG. This one unit, and yeah, the portion of the whole configuration. So actually, I found this this configuration as the way some proteins crystallize. So this is, for example, by a pentagon, we can model what's it called, quaternary protein structures, and some quaternary protein structures crystallize in some way as in a periodic fashion. So then we can state the crystallographic symmetry group packing as trying to find a configuration that maximizes packing density with where we optimize over the whole isomorphism class of a given plane group. So the packing density can be, so we have an infinite structure, but for periodic configuration, it can be shown that the packing density is a simple nonlinear function, which is just here. N is the number of atoms, K is the compact set we want to pack, and the unit cell is well, I show it on the image. This is better. So here we have packing, some packing of regular octagons in the plane group P2. So the unit cell is the blue parallelogram, and yeah, so the packing density is the area of the parallelogram, well, number of symmetry operations, modulo lattice translation, which is 2 in this case. So P2 is in fact a semi-direct product of a point group with 2 elements, identity and rotation by 180 degrees, and the lattice subgroup.
Mila, since this is a very important slide with problem statement, could you clarify what is fixed and what is variable in this problem statement? So the symmetry group is fixed. Is it correct?
The symmetry group type is fixed. So we optimize over the symmetry group type associated with so P2.
So
this means that in P2 the optimization variables are the size, the shape of the unit cell. So in P2 the crystal system is given by the oblique, it's oblique. So this means the length of both lattice generators are free. So the size of 1 and 2, then the angle between them is also free. So, and then another free parameter is the position of the center of the octagon in the fundamental region of the P2 group, and the rotation of the octagon. So we move the octagon and rotate it, and then yeah. So this actually boils down to instead of, so the number of symmetry operations for a given plane group is the same, it doesn't change, and the area of the octagon doesn't change also, so that is a constant. So the only thing that influences the packing density is the shape of the unit cell. So instead of maximizing density, we're actually looking for a minimum area of the unit cell. So this on the right is actually the densest packing of octagons. So yeah, we start with, not even start, so we want to get to the right configuration. A quick one slide about the optimization method we used. So we want to have a algorithm or method that's robust to we can use for any crystallographic symmetry group. So in chemistry, chemists are more interested in 3-dimensional so space groups. Then we want to have something that's robust to the shape. So for convex shapes, but in theory also for non-convex shapes. So yeah, that's why we chose a stochastic approach. So instead of minimizing or maximizing the packing density, we recast this problem to the problem of finding a probability distribution that maximizes the expected value of the packing density. So fx is, in our case, is say packing density, and we want to find probability distribution dp theta from some parametric family of probability distribution. So to solve this, we constructed a non-Euclidean transdivision method that searches over S, which is a parametric family of probability distributions. Just on a side note, S has a structure of a dually flat Riemannian manifold, which is nice and allows us to use the standard calculus and gradient methods to search for optima. Another note is about the optimization algorithm that the lattice subgroup of a crystallographic symmetry group induces a Gaussian space, which is homeomorphic to an n-dimensional torus. So thus we restrict the probability distributions to probability distributions defined on an n-dimensional torus. So as an example, this is first iteration of one run on the problem of finding densest stacking of octagons in the P2 plane group. So the P2, so this instance of the plane group packing has 6 optimization variables. The center, 2 coordinates for the center of the octagon in the fundamental region, then the rotation of the octagon, and the phases of the lattice generators and the angle between them. So first we sample, in this case, 600 samples from this distribution on an n-dimensional torus uniformly at the beginning, and then we move the distribution to the distribution that maximizes the expected value of the packing density. So this is the picture on the right is the output distribution, or histogram of this distribution, and hopefully it concentrates on areas of the maximum packing density in this configuration space. So we use ETRP entropic transition packing algorithm on various regular convex polygons in all 17 plane group types, and for n equal to from 3 to 27, and then some other values of n, because we wanted to check some things that we found. And so we got the values of densities and the configuration of densest packing, maximally dense packing, because we don't know if there is any higher packing, since it's a stochastic optimization algorithm. But nevertheless, we got configurations and packing densities of some maximally dense packings, and we organized it into this colored table. So to explain this table, first we have on the y-axis there are all of the 17 plane groups, and x-axis is the number of vertices of a given n-gon, so and a disk. So for example, by fixing a shape, say a disk, we ranked the densities, maximum densities we obtained in all 17 groups, and then we ranked it. So this means that the red rank has the highest density for a disk. Then the orange ones have lower densities, and so on. If the color are the same, the densities are the same. So for example, here we can see that the highest density for a disk are contained in P2, P2GG, PG, P3, P3, and P1. They have all the same densities, and the highest packing densities from all 17 plane groups. Here, so this is a quite nice table because one can see some interesting patterns emerging, and some periodicity in these packing configurations as the number of vertices increases. So we organized it according to the disk packings into 4 groups. So yeah. So the first group is the P2, PG, P2GG, and P3, and P1. So what's and some examples from these configurations. So from the top to bottom, it's a pentagon, heptagon, anagon, which is a 9-vertex n-gon, and a dodecagon, 12-vertex n-gon. What we found is that the densest packings, for example, for pentagon, in the densities in P2, P2GG and PG were equal approximately. And if one looks at the configuration and forgets about the plane group, they are basically the same configuration. The same goes for heptagon, and actually it works for almost all n-gons except for n-gons with 3-fold rotational symmetry, no central symmetry, and for n higher than 9. So, for example, for the anagon, the densest packing configurations in P2, P2G, PG, P2GG, and PG are not the same. So the highest is obtained in P2, then in P2GG and PG. But as only but the densities, also the configurations, equal in for the anagon in P3 and P1 configurations. So, and yeah, for the dodecagon, the densities are equal in all these 5 plane groups. And again, if you forget about the plane groups, the colors, and the configurations are basically the same. So what we found is that this works for all n-gons with 6-fold rotational symmetry. So and also the disk. So in some sense, the n-gons with 6-fold rotational symmetry, or the packings of n-gons with 6-fold rotational symmetry behave like a disk, or the densest packing, to be more precise. Just to show the evolution of the packing density as the number of vertices increases, one would expect the packing density with increasing number of n converges to the packing density of a disk, which is denoted by the red line. But what's interesting here is that you can see that for n-gons with 3-fold rotational symmetry but no central symmetry, the 3 P2, PG, and P1 are different. So this works for 9-gon. Also, here is the 21-gon and 15-gon, and also if one goes higher, this is a 39-gon. And yeah, another thing is that there is a conjecture, a two-dimensional version of the Ulam conjecture. So the Ulam conjecture states that the optimal packing of spheres attains the lowest density out of all convex shapes. So any other convex shapes and optimal packing of this shape is higher than the optimal packing of a sphere. So, for example, by taking a tetrahedron, the optimal packing should be higher than that of a sphere, of the face-centered cubic configuration of a sphere. So the two-dimensional version is that this minimum is attained by the heptagon. So the 7-vertex n-gon, which is here. Yeah. So yeah, the heptagon. So yeah, we can see that the heptagon actually, at least from the n-gons, we for the packing densities we obtained, attains this conjecture holds. Now we come to the P2MG and CM and P4 packings. From the top to the bottom, there is the P2MG, CM, and P4 packings of the heptagon and decagon, which is 11-vertex n-gon, and the dodecagon. First, so the P2MG and CM packings are for the heptagon are the same, and yes, this is in fact the same configuration, and this turned out to work for all n-gons except for n-gons that are close to 12-vertex n-gons, so 12, 24, 36. So for some reason, so this is an example of an decagon. The P2MG and CM packings are not the same, and P2MG is higher than the CM packing. And this also holds for 13-gon and 24, 23, and 25-gon, yeah, and so on. Then for the decagon, the P2MG, CM, and P4 packings attain the same density. However, in the P4 group, the P2MG and CM configuration are not isometric to the P4 configuration. So one can see this by the organization of the hole, bigger holes in these configurations in P4 and CM, for example. There is another way to show this, which I will come to later. And so this equality between maximally dense packing configurations in P2MG, CM, and P4 plane groups holds, at least experimentally, for all n-gons with 12-fold rotational symmetry. And that includes also the disk. So here's the evolution of the packing densities in P2MG, CM, and P4 configurations. I will keep it that. I want to talk about something else. Yeah. Third group is P4GM, C2MM, and PM, and P2MM configurations. So for PM and P2MM, the packing densities are the same for all angles. Then for the central symmetric angles, the C2MM, P2MM, and PM configurations are the same. So this is the decagon. No, this is the octagon. Decagon is, yeah. Yeah, so C2MM, P2MM, and PM configurations are attain the same density, but if you notice, the PM and P2M and P2M configurations are not isomorphic. So this is the decagon are slightly rotated compared to P2M and C2M configuration. On the other hand, I didn't have images of this, but there are two non-isomorphic configurations, P2M, PM configurations that have the same density, and one that is actually isometric to P2MM and C2MM configurations. And for the octagon, all four plane group packings are attain the same density and yeah, basically the same configuration. And this works also for all n-gons with 8 poles rotational symmetry. This. So the last group, this is the five last plane groups. There were all the packing configurations are different. So the highest is the P6, then P31M, P3M1, P4MM, and P6MM. So yeah, within this group there were no relationships. However, there are some relationships that cannot be seen from the rank table, that I will talk later. Yeah, the evolution of the densities. So yeah, based on these results, we stated 3 conjectures about the optimal packing densities of for all regular n-gons. So the first one is about the P2, P2GG, PG, P3, P3, and P1 plane groups that states that for all n-gons, the P2, P2GG, and PG group are the same. So densest packings for all n-gons differently. All n-gons attain the highest packing density in P2, P2GG, and PG group, except for n-gons with 3-fold rotational symmetry, no central symmetry, and for n higher n equal to 9. So 9, 11, 21, 15, no, yeah, 9, 15, 21, and so on. Then for centrally symmetric n-gons, P2, PG, and P2GG, and P1 densest packings are equal, and for 6-fold rotational symmetry n-gons, P2, PG, P2GG, P1, and P3 are equal. Second one is about the second group, P2, MG, CM, and P4. So for P2MG and CM, the densities in P2MG and CM groups are equal for all n-gons except for n-gons with 12k minus 1 and 12k plus 1 rotational symmetries, which are 11, 13, this is 23, 25, and so on. What's also interesting is that, in fact, so usually the P4 has lower density than the P2MG and CM, but in these cases, the density is higher than the P2MG and CM packing configuration. And about the third group, P4GM, C2MM, PM, and P2MM configurations. So for PM and P2MM, for all n-gons, P2 and P2MM packing configurations are equal. For centrally symmetric n-gons, we add C2MM, and then for eightfold rotational symmetry n-gons, we also add the P4GM configuration. So, as I mentioned, for this P6, P3, 1M, P3M1, and P6MM and P4MM, there were no relationships directly can be observed directly from the packing densities. However, we were able to get some relationships between groups within plane groups in different classes. So, for example, for a hexagon, we find the relationships between P2GG, between this class and P6 and P3M1. For example, by comparing these packing configurations, for example, in P1 and P6, can notice that only one hexagon is missing, and there are 6 of them. So the density of P1 is 1. So we can get ratio between P1 and P6, and similarly for the P3M1. In a similar way, there are 3 octagons missing, 3 hexagons missing in this configuration, and also for relationship between P3-1M and P6-MM packings or hexagons. For example, by noticing that these 2 configurations, somehow there are 6 hexagons missing in all of these big holes. What we also found is that numerically these relationships hold for all n-gons with 6-fold rotational symmetry. So for 6, 12, 18, and so on. Now we can do this same for an octagon. This is more tricky, but one can, by counting the empty spaces, like the complement to the packing configuration, and also here we can compute the complement of this configuration just by so for example, these are squares with the edge length of the octagon, and then we can compare these 2 packing configurations, actually relationship between P4MG and P4MM, configurations. And then we found that this works for all, and numerically, this works for all n-gons with eightfold rotational symmetry. And for the 12 vertex n-gon, a similar thing can be done between P1CM, P4GM, and P31M configurations. So, and again, numerically, this holds for all n-gons with 12-fold rotational symmetry. So we don't have a proof that it works for all n-gons with this, like for the 12-fold or 8-fold rotational or 6-fold rotational symmetry. But I think it can be done. But let's assume it works. So then, it should work. So all these relationships should work for n-gons with 24-fold rotational symmetry. And yes, at least numerically, it does. So for n-gon with 24-fold rotational symmetry, we get relationships between all of these, all of the densest stacking plane group configurations. Now, using these relationships, since the disk contains 24-fold rotational symmetry, and plugging in the value of the densest disk packing, which is attributed to both Lagrange and Gauss, we can get all densest exact values of the densest packings of densest plane group packings of a disk. So here, so yes, this is what we know, densest P1 packing. So the lattice packing configuration, which is this value square root of 3 divided by 6 times pi. And the first proof of this, of the general optimality, so Lagrange and Gauss, it can be shown by the results of Lagrange and Gauss that the optimal lattice packing has this value, and this is actually the lattice optimal lattice configuration. But about 100 years later, there was a first proof, complete proof, that this is the optimal lattice, optimal general configuration. I mean, in the space of all two. Now, the proof is was given by Tejes Tóth, an Hungarian mathematician. So one other thing to mention is that to every disk packing, one can associate a regular tiling by taking the centers of the disks, and if two disks touch, one creates an edge. So we have the middle image is the regular tiling associated with the P1 packing of the disk, which is a triangle packing by taking the triangles in this configuration with triangles. And in the opposite direction, we can get a disk packing given this regular triangle tiling just by taking the vertices of the tiling and taking a disk with the radius of half of the edge length of the triangle. And then we can, so this classification of these regular tilings based on the type of vertices. So these configurations have only one type of vertex, which is denoted by 3, 6, which means there is 3 is vertices of a regular polygon. This so 3 we have a triangle, and 6 triangles touching at the vertex. So yeah, clockwise. So that's that. And to a given tiling, we get the dual tiling, the same as dual graphs are constructed. So this, by forgetting the colors of the tiling, we get the geometric graph and the dual graph by taking the vertices as the faces, and then the edge between the faces. There is an edge in the dual graph. We get the dual graph, dual tiling to the regular tiling, which is tiling by hexagons, and in fact we can get the packing as constructing inscribed sphere in all of these hexagons. So in other words, the hexagons are the Voronoi cells of the, or yeah, the tiling is the Voronoi diagram of the disk packing. So then plugging in the values, so the optimal disk packing into the relationships of 24 full dimensional n-gons, we can get all the exact values of all the n-gons and then associated this. In this case, this is a semi-regular tiling, and it's the same. It's not by the same polygon. So there are triangles and squares. However, property that there is only one type of vertex in this tiling state. So in this case, we have 3, 3, and 4, 2 vertex type, which means 3 at every vertex. There are 3 squares and 3 triangles and 2 squares. And so these tilings are called also Archimedean tilings, because Archimedean polyhedra share the same property, which means there is only one type of vertex in this on this polyhedra. So this is the P2MG of all P2MG configurations of the disk, and another this is a P4 optimal P4 configuration. They have the same density as I mentioned previously, but from here, this is actually the way to show that these configurations are not isometric. So although they have the same density with P4 and P2MG, the associated semi-regular tiling is different. And yeah, same way we get can get exact values of all plane group packings of a disk. Yeah. This is for P3M1, P4MM, and the associated semi-regular and dual tilings, and P6MM. So I did this in in October 2022, and I couldn't find any exact values of these disk packings. I could only find numerical approximations. So I thought I've found something interesting, but as I prepared this talk last week, I actually found a book from the 1979 containing all of values. Yeah, so that's a bit of a disappointment, but in this they're just all and and without any reference. So there is hope to get it. Yeah, to finish this. So thank you for your attention.
So, thanks, Milo. Let's all thank Milo for a great talk. And yes, and also one that is pretty much giving us plenty of time for questions. So, would anybody like to ask, anything? Either in the chat. I'll stop recording first. That would be